to have with me Dr. Paul Debevec, Senior Staff Scientist at Google Research and Adjunct Research Professor, USC, Computer Science and USYD, USA, joining us from Los Angeles. Hi, Paul. And I'd like all of you to welcome Dr. Mike Seymour, Research Lecturer and Writer and a Tech Specialist in Digital Humans from MOTUS Lab. And he's also the FXguide co-founder, and he's joining us from Sydney, Australia. Hi, Mike. I'm R.K. Chan. I'm the head of studio at Technicolor Film and Episodic VFX in Mumbai, at TraceVFX, and an ever enthusiast of CG, computer graphics, and the kind of work that researchers and fabulous scholars around the world have been doing. I'd like to begin this session by a small intro on the kind of work that Paul and Mike both have been doing, so that we set the context for the panel, and then I'll hand over to Mike to take over this discussion with Paul on the lovely journey on digital humans. How many of you guys remember that small video clip playing down below from this little unknown movie called The Matrix? And how many of you are computer graphic nerds like me and remember the Campanile movie of the Berkeley University and were wowed back then when we saw this? Paul Debevec, the man behind all of this, he began his career by developing new ways to create 3D models from photographs, starting with an image-based model of a Chevette automobile in 1991. At the University of California, Berkeley, he developed the facade architectural photogrammetry system and used it to produce the Campanile movie, showing a photoreal flyover of the UC Berkeley campus for the SIGGRAPH 97 electronic theater. I remember going back and forth and trying to see if this was an aerial footage or not. And this brings up really nostalgic memories of back of those days and early 2000s and late 90s. He then advised on applying these techniques to create virtual background for famous bullet time shots. Those are the ones that you see down in the bottom from the famous movie, The Matrix. In the late 1990s, Paul developed the technique of high dynamic range image-based lighting, or HDRI, as we all know in the CG industry and VFX industry, where HDR panoramic images are acquired on location and then used to illuminate computer-generated objects, making them appear as if they were truly in the scene. Remember those chrome balls and the amount of days that you spend on the shoot with those chrome balls? You can all thank Paul for that. Paul created 2 films, Rendering with Natural Light and Fiat Lux, to demonstrate this technique, which is now a standard visual effects process for film and television visual effects. For the last 20 years, Paul has developed a series of Academy Award-winning light stage devices which surround actors with computer-controlled LED illumination, their original design to perform real-world image-based lighting on actors for photoreal compositing in virtual environments. And it is now a core technology component in the revolution in the virtual production techniques of today's world. Light stages have also been applied to digitizing human facial appearance in high-resolution facial scanning. Some of you guys in the audience from India might remember a movie called Robo. And Paul, you do remember Robo, right? And the scanning that was done back then. And we had Srinivas in my panel yesterday, and he mentioned about what all he has done. And this light stage, I remember the amount of work that he did using the light stage there. High-resolution light stage facial scanning enabled in 2008 Digital Emily project, demonstrating one of the first photoreal digital actors, and in 2013 Digital Ira, one of the first real-time photoreal digital actors. The light stage facial scanning process has now been used in over 50 feature films, including photoreal digital actors in Avatar, Furious 7, Blade Runner 2049, and Gemini Man, as well as numerous video games and television shows. Thank you, Paul, and it has been an honor to have you on this panel.
Thank you. It's awesome to be here.
Thanks, Paul. I'll move on next to introduce our dear friend and the accolades that he has brought in over the last 20, 25 years on his work in the field of CG and VFX. Mike began his journey in visual effects writing code. Don't get confused by seeing the photographs in here. He has background in other adventures as well that you can very well see, but he then worked as a compositing artist. He was nominated for an Emmy and won an AFI award before he moved into consulting and training. Mike has a degree in pure maths, a master's and a PhD, all from the University of Sydney, where he has a research lab today. Since 1999, he has also been one of the co-founders of FXguide.com, which is a leading industry site highlighting the incredible work done around the world of VFX. FXguide has served for over 20 years as a bridge between hardcore research and artists working in the field. FXguide regularly gets over 2 million visits a year and is one of the most trusted sites for helping to explain and illuminate cutting-edge visual effects and animation. It was in this capacity that Mike first met Paul Debevec and published first of many stories involving his incredible research on FXguide back in 2005, which I'm sure Mike will take us to the journey about his friendship and his work with Paul over the last 2 decades. In fact, it was Paul's work that inspired Mike's PhD thesis into digital humans. Mike's work today is particularly focused on interactive real-time, realistic digital humans, and with Paul's help and that of the lab at USYD, Mike himself was scanned and turned into a digital double, which was then converted into a real-time interactive SIGGRAPH presentation known as Meet Mike with Epic Games. Over 5 days, Mike, as his digital human version, met experts in virtual world, and one of those experts was Paul himself. While Mike now consults to several effects companies and Hollywood studios, he is also researching ways to take this technology and apply in other areas, such as helping people with brain injuries. Mike joins us from his MOTUS lab in Sydney, which looks like the background that he's sitting in, I guess now. Looks lovely, Mike. And Paul from Los Angeles. Over to you, Mike, to take us through the journey of digital humans.
Thanks so much. And I'm sure I speak for Paul when I say it's a great joy to be joining you guys today. I've certainly got fond memories of India and have been there a few times. In fact, yeah, my father was actually born in Sri Lanka, of all places. Most people don't believe me when I say that, but you know, he was, even though. And so, Paul, you and I have, well, you've been on this journey for quite some time with digital humans. I kind of tagged along for a bit, but we've definitely seen quite a transition from different types of techniques and different types of approaches, all towards trying to get realistic digital humans. I guess I was going to ask you to start off. How far along that journey do you think we are? How close are we to just saying we've solved digital humans?
Well, I think a huge event happened, you know, in late 2008 with The Curious Case of Benjamin Button and Digital Domain's great work in creating the old version of Brad Pitt for that film. That was the first time in a feature film there was a leading role for most of the time as a digital human, and it worked, and it holds up pretty well today. So that was,
the first 52 minutes of that film, there was no actual Brad Pitt, which is just remarkable, right?
Yeah, it's amazing. That seems like it actually happened several years earlier than it really had any right to. The yeah. Folks were on point with that one. And you know, most recently, Gemini Man. It's got a digital young Will Smith. It's got a digital current age Will Smith for a lot of the shots. It's probably our next, high watermark for this technology. So yes, we can get over the uncanny valley where things are not quite yet available. It's not easy or cheap to do. These are very bespoke digital human characters that can cost just as much to have in the movie as the original actor. And so getting this to where it can be used reliably and without risk in an economical way in a much broader class of productions is where we're going at this point.
I think the other thing that is worth sort of mentioning, and I think it happened faster than it had any right to, was getting really good quality real-time digital humans. Because certainly a lot of my research concerned these days about interactivity in real time. And I was doing some stats on that when talking to some friends at Pixar, and they were really enthusiastic because they got their kind of average render time down from 25 hours to 2.5 hours for a frame. And we had to get stuff done in 9 milliseconds. And so to give you an idea about that, you can fly from London to Rome in about 2.5 hours, and you can get basically 4 meters in the plane in 9 milliseconds if you're kind of going well. So the amount of time you have to render in real time is not just a lot less, it's an astonishing fraction, if you sort of do the math. And yeah, I don't know if you'd agree, but it's remarkable.
Absolutely remarkable. And it just pulls your head out of thinking, like, you can't think of the problem as being a particularly hard one because you don't have enough cycles to solve a hard problem or to render a hard thing. And that's something I think always is helpful, is if you can just briefly not let yourself imagine that the problem is hard. Everyone thinks it's hard. You think it's hard. You just put yourself in a different brain space. You don't let yourself think it's hard. Sometimes you'll find a way that you can actually do it in a much simpler way. For me, it was our digital IRA project in 2013, which was a collaboration with Activision and Javier van der Pelen's team over there. He put together some of the best facial animation people and real-time shader writers that pulled the thing off. And it was another case where we did like the best darn face scans that we could, delivered the data, corresponded as nicely as we could. And then when we saw the first renderings come back, and just had to ask several times to be sure, wait, this is real time? This is, oh my God. So I don't think every video game has photoreal characters in it. Particularly like when you're actually in gameplay, they tend to be a bit lower resolution. It's nice if you can have your entire PlayStation 4 just looking at that one asset. And once you're in a huge environment, you kind of have to dial it back. But hey, PlayStation 5 is on the horizon, and I'm sure there are people who are working very hard at making sure those faces look great all the time.
Yes. I think what we might do, just to help people, if it's all right, is we're going to just do a bit of a trip down the path of how we put together the Meet Mike project, because that'll let us illuminate this, I guess, first fundamental aspect of digital humans, which is what we're now calling the classic way of doing digital humans, albeit like from a year ago. But it's what I just think of as this kind of model, texture, light, and render. And in exactly the same way as somebody would do a house. They would, model a house, they'd put the textures in, they'd light it, and they'd render it. And that path, that traditional CG path, has its own history, of course, with digital humans. But if we can just lean in, if you don't mind, on Digital Mike, let me share with you that, because it'll, for people that don't know, it'll explain the process. And of course, it was fundamentally Paul's work with the team at USC. So I'm just going to share that right now. So this is, we're going to be like looking at stuff that we were presenting in 2017. And then later in this hour, we'll actually show you some more current stuff. But this is a really good idea of where that was at. But I should say that Paul's been doing this for a fair while, and I've been lucky enough to know Paul for a fair while doing this. So we have lots of photos, him and I bumping into each other in all parts of the world, including, I think, a good shot of you there at the Oscars. One of the several times the Academy rightly honored Paul for his brilliant work. Anyway, so that's a shot of us. Paul, which light stage are we in here?
This is light stage 6.
Which was incredibly impressive. but it sits in a history of light stages. And we're not going to go through that, though I would recommend that you look at Paul's website. He has a terrific sort of documentation on all the light stages. But yeah, I was lucky enough to be in many of your light stages at various times. Here's me in 3 different ones. And I kind of lose track almost. But the thing that happened is that we were involved in this group, some of whom are in the top right corner there, to put together a sort of a wiki-human, digital human project where we would allow the community to take the data of scanning my face. And so our good friend Chris suggested me because people knew me and they thought, well, you know, let's use Mike. And so there we go. And so I think that's down the bottom there. That might be at your new company, Paul, I think, not at USYD. But anyway, so this is what the project was, the classic pipeline of modeling, texturing, lighting, and rendering. And so for those of you that don't know and or haven't maybe thought about it, there are 3 aspects to a digital human. We have to make a digital human. We have to make that digital human move, and then we want to render it or produce it as a footage that someone can look at. So let's have a look at that now. So that was a shot you'd have seen before. Paul, do you want to explain what they're looking at here?
Yeah, you're sitting inside Light Stage X, which actually still runs at USC Institute for Creative Technologies in Los Angeles, and it's the flagship facial scanning device. You're surrounded by 346 bespoke LED light sources. These are using the white LEDs. It can actually do 6 other spectra of illumination as well. But it's about to do a face scan, in which point it's going to light you with a series of lighting patterns that kind of concentrate the light into different cardinal directions, up, down, forward, back, left, right. And for each of those, it'll take 2 photographs, one that's polarized and one that's unpolarized. We have different polarizers on the lights that can turn different LEDs on, and we have fixed polarizers on the camera in a vertical orientation. And essentially, this allows us to image your specular reflection and your diffuse reflections independently, which has a bunch of advantages when you're making a digital human.
So there are 2 things that the light stage is really giving us here. Firstly, because it's taking my photo with different cameras and stuff, it can obviously reproduce my head, and we'll go into that in a fraction more in a second. But it's not just a still of me in one position, it's building a model of me that can be animated. And so while you've got these multiple views that Paul was just referring to, in fact, get me doing multiple different facial expressions. This is just a subset of the embarrassing poses that I did. Did you have a kind of a standard set or a number of these? And do you want to explain what these fax things are, Paul?
Yeah, I think we went even more extensive for you because this was sort of like an academic research data set. But when we first collaborated with Image Metrics in 2008 for the Digital Emily project, you know, they had some really top-end facial modelers and riggers. And so they had a set of 30 different facial expressions that are based on, in part on Paul Ekman's facial action coding system, just trying to isolate different muscle groups. Then you can combine those to make the different emotions and mouth shapes that you might need. And we still to this day, call that a Digital Emily data set. So we gave you like the executive Emily data set, I think.
Okay, and so this is a really interesting picture because it shows one of the properties that of why Paul was talking about having different types of light and different types of polarizers. And Paul, I'm going to, if you want to talk about this in a second, I'll zoom in on just the eye to sort of explain it. But maybe you could just run through what we're looking at here. Yeah,
certainly. Well, so when light hits a human face, some of it will end up getting absorbed. We don't reflect back all of the light. But the light that reflects, one of 2 different things happen. It either reflects right off the surface without going into the skin. And that's the specular reflection or the highlights or the shine. It stays the color of the light source. And it's a view-dependent effect as you view the face from different angles. It also happens to maintain the polarization of the light. So if you send in polarized light, the specular reflection will stay polarized in the same direction as it reflects off. The basic, texture map of the face, or the albedo, the skin coloration, is the result of the light that gets under the skin and then bounces around a little bit. It will go through multiple scattering and somewhere within, 0 to 1 millimeters further away from where it came in, it will reemerge in some random direction, and it will have lost its polarization, and it will have picked up the coloration of the skin. And that can be, different, browns and reds and pinks and all sorts of different skin colors that you'll see there, some even on the same face. So normally when you take a picture, you're getting a mix of the specular and the diffuse. It's very helpful, just like if you're recording a rock band, you might want to have the guitar and the drums and the vocals on separate tracks if you're going to try to remix them later. It's great if you can get the specular and the subsurface components on separate tracks and separate images if you're going to then try to render the face in new lighting conditions. And there's another really nice effect, which is the specular reflection has a lot more detail about the skin pore structure. Since it doesn't blur out due to subsurface scattering, you can actually measure the shape of the face quite a bit more accurately. And that's how our face scanning process at ICT measures the face down to sub-millimeter detail.
So looking at this picture now, what we're seeing is, zooming in on the previous picture, you're seeing that skin detail. And if I go in one more level, I think this is really informative, because the normal picture that just you would think about if you took it on an iPhone, on the left there, has obviously the spec and the diffuse. When you split them out, you'll see, if you look at the eyeball, there is no highlights on the eyeball, because those highlights are, of course, specular highlights. And that's exactly what gets isolated into the spec and not appearing in the diffuse. And similarly, I don't look like I've got many wrinkles in the diffuse, because that kind of stuff that I perceive as wrinkles is to do with how the surface is sort of, being with age, changing. And that's really something that we're getting from the spec. And so when you only look at the diffuse, you of course don't look like you have wrinkles, which is why many people wear makeup, because they get out the sort of the dusting of a foundation and it removes specular highlights, and voila. So if you ever asked at a dinner party why people wear makeup, the answer is absolutely contained in Paul Debevec's SIGGRAPH paper. Okay, so moving on, that is just put together a head, and that head has to have some more work done on it, but we're going to get the textures out. We don't just get the model. But having said that, the model that we get out is a marvelous model, but we're going to get those models out, Paul, aren't we, for each of those expressions. Mm-hmm. And so we get the texture, and we get the models out. And then, Paul, what are we going to do? I mean, what's the stage that happens after that? Because we need to sort of connect these up.
Yeah, since your face moves around, each one of the 3D reconstructions that's done from the 8 cameras that we have, and something that's similar to a basic photogrammetry process, it then gets refined using the specular surface orientation information to get the sub-millimeter detail. But they're not topologically consistent. These meshes are made out of triangles, but the triangles end up in all different orientations around the face, depending on which scan it is. And what we want to do is make it much easier for animators to blend from one facial expression to another, or even take linear combinations of 3 expressions over here and 2 expressions over here. So they need to be corresponded onto the same space. And this square image that looks like something unfortunately rolled over you at some point.
Roadkill, Mike, yes.
It's probably your neutral expression, and it's just kind of laid out by an artist into a standard configuration. And then there's a process wherein we have to take all the other expressions and get them lined up so that they lay into the same place, except the texture map will be different. It'll show some of the blood flow in the face because you've squished a cheek up here and then the coloration changes. Each one of these will also have like a normal map, a displacement map, a specular map that goes along for the ride. And those will show off the different wrinkles when you go into the different expressions too.
So here's one of the first images that we got, and they're just temporary eyeballs. So if you ignore the eyeballs, you'll notice also that the hair is not actually there yet. But yeah, without looking at the hair, because we haven't put it in, and without worrying about the eyeballs, which we just put in there so that it wouldn't look freaky, you can see how remarkable the CG version on the right is compared to the one that, that was actually a photo of me in the same day on the left. And Paul, you must have, at some point first seen one of these and just been staggered yourself at how well they've come up, because I've got to say, this is really, to me, near magic how well these maps and obviously the samples have been done, and they're very mathematically accurate.
Yeah, I think the first time is when we were doing some of the, just before we would do some of the scans for Avatar. So, you know, our good friend Mark Sagar, who's amazing, you know, facial animation and behavioral modeler from New Zealand, was visiting our lab just as we were doing our very, very first high-res space scans based on this polarized specular illumination. And conveniently, he had just taken a job at Weta Digital, which conveniently had just been awarded the contract to do James Cameron's Avatar. And I think 3 weeks after that visit from Mark to our lab, we had Zoe Saldana and Sam Worthington showing up for the first space scans that we ever did commercially. It was a bit of a scramble to get it ready for that.
Okay, so now that's sampling. That's literally determining what the face looks like. And as we said, built so that it could be animated between expressions. We now need the rig to actually do that, because obviously what we're not trying to do is just have me deliver the one line. We want to be able to have me say any line. And so you end up with an underlying head rig. And so the head rigging is, I think to this day, one of the least appreciated parts of the process. The rigs and how the rigs work is, we'll give you an idea. If you were to go and see a major Marvel film, and a lot of studios work on those, the one thing they'll never trade with each other is their rigs, because they're all custom. They'll swap a ton of files. But if ILM hands Framestore a rigged character, their face rig just be tossed away and they'll start over. This is like really an incredibly important part of the exercise. Anyway, we rigged up Mike's face, and then we wanted to try and take it into real time, because we had it and we wanted to see if we could move it in real time. And so this is some of the first attempts at getting the data that Paul had so generously provided from his team with a three-lateral rig, three-lateral now being part of Epic, into a UE4 version of me. And so this is, so it's promising, didn't look very good yet, but it was a start. And then we got it actually working. And also we got the ability to, you know, take advantage of the fact, as I said earlier, the two things that we loved about the stuff from the light stage is it not only helps you animate something, but it allows it to be relit in whatever direction. And that's, of course, what we need to be able to use it interactively. So this was it. This was, for us, the first time we saw a relatively real-time render. This is actually still taking 26 milliseconds a frame, which is not the 9 we were aiming at, but by gosh, it was a jump from where we were. And so even though I look a little stoned here, or at least a little concerned, I think I have resting bitch face, Paul. but anyway, yeah, it was
you're a little stoic, and you know, your pupils are also a bit contracted because, you know, it's a bit bright in the light stage, so we get very good views of, like, you know, the full version of the iris before it dilates for that. That's something that ideally one would animate to be appropriate to the situation.
Yes, yes. And in fact, I got my eyeballs done by our friends at Disney Studios Research in Zurich, who did exactly that. They modeled my eyes with different forms of illumination. And I don't have those images here, but if you saw them, they look a lot like, I don't know if anyone's seen the movie Clockwork Orange. That's probably the closest approximation. I was like, my wife thought I'd been in a car accident. Anyway, now we need to drive that rig. And so there are various forms of head rigs. This was the first one that we prototyped. It's actually got 2 cameras at the front. And this is now nothing to do with producing a digital version of my face. It's now trying to interpret what my face is actually doing so it can drive the rig. And there are many solutions from this, cubic motion, faceware. You can even do it on your iPhone now. And depending on which one of these you use, you get a lot more fidelity and a lot more accuracy in being able to drive that underlying rig.
Yeah, and this is really one of the huge achievements of the Meet Mike project, is to not only render the face in real time, but to drive it in real time with live performance, which hadn't been done before with light stage data. Yeah.
I should also point out that the guys wanted me to shave my head because 75% of the geometry was my hair. And they were like, can we get rid of it? Hi, I'm Mike. Well, kind of virtual Mike, really. This is our Digital Human project, which is a collaboration of a whole lot of companies: Epic Games, 3Lateral, Cubic Motion, Tensun, the Wiki Human team, Sydney Uni, FXguide, a whole bunch of people coming together to produce, well, a virtual human. And not only a virtual human, but one rendered in real time, puppeteered or driven in real time, rendered in real time, and not only that, but at 90 frames a second in stereo in VR. So at that point, I'm going to just stop for a second with sharing because I'm keen to get some more info from Paul. But that was 2017, and that is I guess not. There's nothing that's absolutely standard, but it's a sort of a sensible way that digital faces were made. I think you'd agree, Paul. That was sort of like that, and going into real time made sense, and it was a fairly what we now would call classical approach to it.
Yeah, absolutely, and I think we've seen echoes of that as well in Digital Domain. Did the Digital Doug project for the TED conference, where they also added in body capture as well, so you could actually walk around and puppeteer a photoreal version of yourself in real time. We've seen some of the game studios demonstrate versions of very realistic characters that are done from high quality scans done in real time as well. And the movie studios are continuing to this, like the Irishman, for example, didn't need to be rendered in real time, but it also for the older versions of or the younger versions of the major stars, they started with light stage scans and then artistically de-aged them. So it's the way things are going on at the moment, but there might be other things on the horizon.
Yeah. So at this point in time, we really have kind of two sort of new paths that we want to discuss with you guys. The first one is, not in any order, I should add. The first one is, hey, can we try some different approaches to this, which is the non-classical approach? And then secondly, as I said to you earlier, a key stage in this is like how I view this material. And a key area that Paul's been involved in addition to building new light stages and stuff, has been light fields. And so I'm going to, in 1 second, discuss the neural rendering that we've been doing. But Paul, just before we get to an in-depth thing, can you just give an overview of where you're at the moment with this research?
Yeah, I've been fortunate since joining Google a few years ago to get to work on with some very talented people and larger, more distributed teams on things that are some extensions of both the work on the light stages, in particular, applying those to full body relightable capture, that's multi-viewpoint, as well as a project that's more focused on the environments that you might want to put your virtual actors in and then see in virtual reality, which is based on light fields and light field video. And, the light stages still have an array of light sources, and they're getting more and more cameras to them. Light field rendering and capture is interesting because it generates novel views of a scene that lets you do virtual camera moves throughout, based directly on images, even without explicitly going to a 3D model of the scene. So it's a very image-based approach.
Okay, so what we're going to do now is I'm going to show you a bit of stuff about neural rendering. Then we're going to come back and look at Paul's relighting project, or relightables project, which is astounding. And then show you how those two may, in the future, be connecting up with new forms of virtual production. So if you'll indulge me for a second, I'm just going to go back to my slide deck and show you a couple of things. Now, the first thing is an example of neural rendering that you might think of as being something like deep fakes, but we don't call it that because that's just one minor application of it.
I'm Sean Bean from Lord of the Rings and Game of Thrones and The Martian. I think this is brilliant. This is unbelievable, isn't it? I'm an actor, but also I support Sheffield United, the Blades in the UK. Actually, I have a tattoo on my shoulder that says 100% Blade. Blade's the nickname of the Sheffield United football team in the UK, and I'm very proud of that. I'm very proud of the team. I think they probably are the best team in the world. Yeah, definitely. I'm very proud of them. Can I get a cup of tea, love? Yeah. No, mug's fine, yeah. Just don't chuck it. Thanks.
Okay, so the thing about that is we never built a model of Sean Bean's face. We certainly could have done a better job at picking the actor that was playing him there, but and it's obviously limited by my ability to produce an accent. But the point is, the computer is inferring what Sean Bean's face would look like under the lighting conditions that my face was under, at the angle that my face was at, with the expression that my face was at. And unlike what you've seen up until now, this inference is basically like a good guess. And a good guess, when we say, hey, here's a bunch of pictures of Sean Bean at different angles, in the way that you might say to an artist, learn by looking at this model and then paint me a version of that, that figure from maybe a different angle in a different location. And in exactly the same way that a painter would maybe, if they were very talented, be able to do that, the computer is not building a model, not texturing it, not lighting it, it's just inferring it. Now, that means there is no 3D data that we're feeding it. We're feeding it a bunch of training data. And of course, this is the world of machine learning, or AI, I tend to call it machine learning. And so when we take this technology, we are doing something very different from what we've done before. So I'm going to play you one more quick clip that'll show you a different application of the same thing, which is de-aging.
So I'd like to go back about, oh, I don't know, 3,752 days when I looked like this. This is the younger version of me, and it's based on some footage that we had of me 10 years ago. In fact, here's a still of what I looked like 10 years ago. The system is going to learn from training material from this original clip that we have to work out what I should look like today. A lot of the process is, well, not trial and error, but it's just research. And we think it's really valuable because obviously now we've done it, we've learned so much, we can try and impart that knowledge to you. In fact, let's see how I delivered that exact line 10 years ago.
So
a lot of the process is well, not trial and error, but it's just research.
Not trial and error, but it's
and we
just
think it's really valuable because obviously now we've done it, we've learned so much, we can try and impart that knowledge to you.
I really wish I'd said something cleverer 10 years ago. Okay, so the question is, can we combine those two? And the answer is yes. This is a combination of stuff. So it's a sort of a fairly reasonable 3D model of me, when on top of which we're going to add a inference of me.
This is a hybrid version of technologies that we've seen before, but never combined in such an interesting way. What you're looking at is a GAN, actually it's specifically a pagan GAN, that's running on top of a digital version of an avatar of the operator. So let's break it down. What you're looking at is a person in a sort of computer graphics standard head rig and a body capture suit, which you can see here. This is the original source, and that's feeding a digital avatar, which is being rendered in a real-time engine. And then on top of that real-time engine, we're applying another layer, which gives us this final quality, which is using machine learning and a GAN. So it's a hybrid of what you might consider to be a traditional computer graphics digital humans pipeline with the sort of cutting edge leading technology in generative adversarial networks in producing this final hybrid image.
So that was coming out of work we've been doing with PinScreen, which in turn is something that's come out of Paul's old USC ICT mecca. I actually was lucky enough once to have a 2-week internship kind of thing at ICT. It was like me and a kid in a candy store. It's just great. But yes, Hal Lee, who headed up that project, followed Paul in that area. But I'm going to stop now because that's where we're going. We're doing this hybrid stuff. But now Paul's separately been doing phenomenally interesting work. I'd like you to talk about that if you could, Paul.
I'll unmute. Yeah, a couple of things here. So let me show a little bit about what one of the projects we've been working on at Google. And let's see if I can do the thing where I'll optimize here. Do we see another screen over here, hopefully? Yes?
Yes, sir.
All right. Well, let's see. This is going to be a glimpse of the latest light stage that I know that's been constructed at Google. We had a certain amount of space for it, and originally we were just going to kind of basically build a copy of the USC ICT light stage. And then we realized that we were kind of just incapable of doing that because we had to try to do something that we learned something new from. And so we actually tried to build it just enough bigger that we would be able to capture both faces and bodies. So this system here has 331 light sources. It's got 2 sets of LEDs, one that can just illuminate faces, focused at the center, one that's for lighting the entire body. And then it also has cameras, some that are on the face, some that are on the body. And then another really magical thing happened, which is that a year after I joined Google, Google acquired a company called Perceptive.io, which was working on volumetric capture systems, and in particular, kind of very high quality custom depth sensing algorithms and hardware for that. And so our teams collaborated to make this volumetric capture system called the Relightables. And what you can see, one of the project leaders here is Christoph, and he wore his very, very best t-shirt and jeans for the day to get recorded in the light stage. And what we're going to be able to do is take a 3D model and put it into different environments. And something that's different than other volumetric capture systems is we don't just put flat lighting on the subject. We actually bounce between 2 different lighting conditions very quickly. Fast enough, in fact, that it can be imperceptible to the person who's in there. And we're seeing those 2. We call them the color gradients. And the 2 color gradients basically light you up to kind of look like a surface orientation map or a surface normal map. One of the gradients has red light, blurry from the right, green light from above, blue light from the front. The second one reverses that with red light from the left, green light from below, blue light from the back. These 2 lighting conditions, if you sum the images together consecutively, it looks like it's just white light from everywhere. But if you subtract one image from the other and divide by the sum of just pixel value for pixel value, you actually get a surface orientation map. And that helps us improve the quality of the geometry, a lot like what we could do with our facial scanning system, but with many fewer images. And also to provide photometrically measured surface normals, which are better for relighting. So what we'll see in a second here is that Christoph is going to get meshed. Some very good meshing algorithms here. You'll see the maps that we get, albedo. There's specular that we get live. And now we've added him into one of the Google buildings we have in Los Angeles called the Spruce Goose Hangar. This is another colleague of ours, Federico. And we've dropped him into where normally we would go for coffee if we did get to go into the office these days, in some of our conference rooms. And we'll have a few more examples. So these are rendered in V-Ray. This is Jay Bush, who's been a member of our team on the light stage for over a decade. A newer team member, Matt Whalen here. And you can just basically change the lighting in the scene and get pretty good relighting with decent, skin luster and such. It's not as high quality as like a digital Will Smith that you'd see in Gemini Man, and you can't reanimate them. But as it turns out, it's actually a technique that allows us to do this very quickly. Somebody just has to come into the light stage, and then all we have to do, let it process overnight, and then we can put this character anywhere that we want and play back whatever sequences that we have.
The miking problem. Yeah, that's remarkable. A thing that I just find really, really interesting about this is that, as we were discussing earlier, like this work with the relightables and the stuff that's happening with light fields is like moving forward in a completely breathtaking way. But what I find remarkable about this is, and I don't know if you feel this way, but it's like, you'd have thought that you'd have run out of things for that light stage to do because you keep on coming up with these amazing ideas for how to use it. And in some respects, there are echoes now of relighting that you were doing back when you first started. But in another sense, it's sort of, you could never have conceived that it would go this far. I don't know, clearly it's like, been a hugely collaborative process, but nevertheless, it must be something that you must stop occasionally and wonder about.
Yeah, absolutely. It's surprising that, the first light stage was built over 20 years ago at this point. I'm getting worried that someday I might be thought of as kind of like the light stage guy or something. But the thing that actually is most interesting for me is that the very, very old school light stage technique, the very first light stage, which was a single light source that spun around and you had to stay still for a whole minute, like a daguerreotype or something. That kind of one light at a time data actually is becoming the most in-demand data for light stages right now, because it's fantastic for deep learning. Having calibrated data sets of faces where the only thing that changes is the lighting lets ML algorithms learn how lighting plays off of faces. And we had a SIGGRAPH paper last year that showed that you can take a portrait of someone and actually, through machine learning, change the lighting in the portrait, even if you've never light staged that person, even if you only have that single photo of the person, because we got enough people through the light stage that it kind of gets it as to if a face looks like this in this lighting, then it would look like that in this other lighting. And so it's like the most old school technique is getting used for the most modern graphics research now.
So let me just jump back for a second. And when you were talking earlier about Curious Case of Benjamin Button, I was talking to the guys that were doing on that, and we were discussing the fact that back then we would do a light probe. We'd sample the light at a particular point, and then the character would walk out of this room into another room, and then you'd sample the light in that room. And that seemed like a great idea because, you know, image-based lighting would solve the problem. And then, you know, they were like, well, yeah, the trouble is when they're walking between the two, they're actually not correctly lit by either. And it's not just an interpolation between the two because, you know, in this room, it's dramatically different until you go through the door, and then it's dramatically different. And so at that point, I first went, oh yeah, what we really need somehow is some way of knowing what the light is like at every point in the room. And then I just stopped thinking about it like that was an impossible problem, but it isn't.
Yeah, first of all, again, like the people who did the lighting reconstruction for The Curious Case of Benjamin Button, which I think was like Paul Lambert and Jonathan Lipp, who are two good people to have doing your lighting. They did a fantastic job. Claudio Miranda, the cinematographer, thought it was totally realistic because they had to take his lighting choices and put it onto the digital character. The easiest thing actually to do, and I did this in my Fiat Lux movie in St. Peter's Basilica, and Digital Domain did this in Benjamin Button, is you can just take your light probes and project them out onto a rough 3D model of the scene, so that as your character walks through, you know, the light has kind of been locally placed into space in a good way. And then it'll actually change direction as you walk through. Now, that won't handle spotlights, it handles diffuse lights that are local. And at some point you would get interested in, well, let's actually capture the entire light field of what's going on. The other time that you might be interested in capturing a light field is if you want to look at all of the possible rays of light that might be within space. And I'll run just one last little video here on some of our latest light field work because it's hot off the press from SIGGRAPH last week. But it's a technique that in virtual reality, sometimes we watch video on these headsets, right? You can actually look around in different directions and see what's above and to the sides. That's great, that makes it more immersive. But all of this VR video typically doesn't adjust its perspective if you move over here or you move over here. And a lot of our sense of the 3D of a scene you get by just kind of even subtle head motions back and forth. And if even a subtle head motion is not mirrored in your visual field for what is being served to you on the VR headset, at least for me, it's an instant source of discomfort and almost turns my stomach a little bit. It's one of the sources of VR sickness. But then when you do get it right, you can get a much more immersive scene. So if I can just run this other video, we actually found a new way of recording scenes for virtual reality that uses a array of cameras, and it's able to produce video for the first time where you can change the perspective after the fact. Do we see the video again here?
Yep.
Hopefully. So instead of just having a stereo pair where you can maybe like just look left and right, you can actually in post-production fly your camera around the scene anywhere within about a meter of diameter, which is about as far as you can lean around in a chair as you're enjoying your VR experience. And this technique, where you can see here, we're like intentionally going a little crazy on the camera moves. There's actually a downloadable demo, free to try on your VR headset if you've got a Rift S or a Rift or a Vive that actually lets you experience these scenes in headset. And I'll just show you quickly our rig. It looks like this. It has a bunch of action sports cameras on a spherical shell. There's 46 of them. They're synchronized, and when you press record, it basically records all the rays of light coming into this spherical volume. And then with our computer vision algorithms, we have really some of the top people in the world working at Google on these problems. We can run this through a machine learning network that creates a representation that lets you move around in the scene afterwards, interpolates and extrapolates the views, and actually is a compressible representation that you can deliver to see on your home PC that breaks it down into these layers. And the place where this may all come together at some point is in the area of virtual production, where you might have real actors who are actually on a set, and then this real world image-based lighting technique of surrounding them with LEDs to get the lighting right is there. But what if you need to drop in some digital extras somehow? Well, maybe you've captured those in the light stage with the relightables. But what about the environment? Maybe it's something that you have had your artist create a game engine version of, but what if it's a real place? What if you can, send a photographer over there to just capture it, and you want it to look a lot more realistic than a photogrammetry model? That's a case where you might want to record that as a light field, and then actually be able to display a interactive viewpoint controlled light field on the LEDs so that you can actually see the parallax as the camera moves around and illuminate the person from the right lighting for where they're standing.
So the simple example I would give, and just to finish up because we're out of time, but imagine that we made a digital person and they were wearing a bright red clown suit. And now I should point, we can't do this yet, but if Paul's vision of this came off, we could have the notional digital character that's bright red walk, theoretically, past me in the volume. Now, of course, they wouldn't be there, but the spill, the bounce red light off their suit would actually be relevant to me in that volume. So this is taking the current idea of a virtual production LED stage and basically making all the fake stuff somehow as just a feat of math exist so that as I walked through the space, I would be affected by it. Now, that's the goal. And I don't think that it's science fiction. I just think we haven't got there yet. But Paul, final words, how long till we can, is that like a 5, 10, or is it 20-year kind of goal?
I think we're going to see stuff like that in about 5 years at this point. We're definitely seeing ramping up due to the pandemic of interest in virtual production. One of the things that I talked a little bit about at the real-time conference earlier this year was the thought that if you had 2 virtual production stages and you had a scene with 2 actors, you could put 1 actor in each stage. You could get them lit the same way. You could do some motion control to translate the camera motion from one to the other, get the cameras to match. But then that photometric interaction could actually be simulated among 2 live actors. You had this great idea of like the person in the red outfit that could be like a digital character producing the illumination. What if we had, cameras viewing the actors from different directions so that you're reconstructing them in real time, and then you can actually basically display a perspective correct version of each actor? It would not only give you the illumination and maybe even some shadowing, but you could actually also get eye lines. And even though, actor 1 would see actor 2, a very large version of them far away on the LEDs, they'd be in exactly the right direction, and they'd see the facial expressions, and then they could act, and you could have 2 people be in the same scene, even though they're in different locations.
So the takeout is we ain't done yet. Well, at least you're not.
Oh.
But I know we're out of time, and I think that, I don't know if we've got time for any questions, but
we have a bunch of really, really interesting questions, but I know we are really out of time. Some of them are around the deepfake and how does the work here compare to deepfake and the democratization of face swapping. But I think that is something for another time. Mike, it'd be a great pleasure if maybe we can have some closing statement from you, and I can wrap the session.
I mean, I guess all I'd say, Paul, is the stuff that we've been talking about with machine learning and deepfakes, which we call neural rendering, is that idea of machine learning is also happening in your world, that machine learning is happening across the spectrum. And so for me, the solution is a hybrid solution that we're moving forward. It's not replacing something, throwing it out in a whole new approach. It's saying, hey, there are some incredibly interesting things we can do here. And we're just only now starting to fold those in. I'm sure Google in particular would be very much in agreement that machine learning is incredibly powerful.
Yeah, absolutely. And I mean, there's certain aspects that it'll be useful for. We've been excited about the ability to there's actually machine learning behind the relatables in terms of how the depth is computed and such. You can whenever there's a tricky to do algorithm that you can just kind of show the computer what the answer should be in enough cases, it'll just kind of figure out how to extrapolate it, and that's a useful thing. I think that these techniques that use machine learning to render faces and generate the pixels rather than a rigged, textured, animated model, I mean, those will get used in movies and TV shows very soon. Most of the major visual effects studios have a crack team that's trying to play with the tools as they are and figure out how to make them useful in production to increase the quality, and then to put those artistic controls that people are going to want as directors ask for changes to be made. So I'm sure that within a year, we'll see the first of these kind of machine rendered faces showing up. They'll be for background characters first, or not that big. And then at some point it might be, the lead characters in the film. And, my cheekiest remark on this is that at some point you just have to take all the scripts of all the movies that have ever been made and the MP4 files of the movie. Then you have the computer learn the relationship between scripts, .txt files and .mp4 files. You have a new script, a new .txt, you put it in, and then it gets out your .mp4, and you can release it in your theaters at that point.
That's amazing. But Mike, I think we are really out of time here. This has been a great honor, and thank you so much, Paul. Thank you so much, Mike. I'm sure we will have an occasion again to carry forward this discussion. And I would like to thank CII and like to thank the entire audience for giving us this occasion for this lovely morning chat from Mumbai, Sydney, and Los Angeles. So signing off. Thank you so much, Paul. Bye. Bye, Mike. Thank you for doing this. Thank you.